Okay, now let's understand few cross-linking condensation polymers. So the polymer which we are going to study, it is going to be something like a phenol formaldehyde polymer. So we are going to study basically phenol formaldehyde polymer. So now in this case, let's try to understand what exactly happens in this reaction. Let's say if you have a phenol like this is benzene ring, and then this is connected to OH. Okay, this is phenol. And then you have something like H, C, double bond O, and then H. You have a hydrogen over here, hydrogen in the ortho position. So what exactly happens is this is partially negative. Oxygen gets partially negative charge due to electronegativity. This gets partially positive charge. Right. So now what exactly happens is this hydrogen goes to this oxygen, and then this carbon comes and get connected over here. So what exactly happens is it follows a mechanism, but I'm not showing the mechanism right now. It's just I'm just showing the direct what exactly happens over here. So basically you have something like OH here, and then you have something like you have carbon getting connected over there, and this is connected to OH. You have this carbon bearing two hydrogens, right? So it is CH2OH. I could simply write this as a benzene ring. Then you have an OH over here. This is connected to CH2OH. Now similar to this, you also have a hydrogen over here. So this could react with HC double bond O in the same way. So the hydrogen would go to oxygen, and then carbon would go and take its place. So what do you get? You get the same thing over here, CH2OH. Now there is one more ortho hydrogen over here. So the same thing could happen here also. You have HC double bond OH. So as we already know that this hydrogen is removed and it goes to O. So this hydrogen goes to O, and this carbon gets connected over here. So it forms something like CH2OH. Now when we are discussing the mechanism, what exactly happens is this bond comes up and it gets bonded to this particular carbon. Then hydrogen gets transferred. So it is something like this. You have a benzene ring over here. Okay. Now this bond, this bond comes out, or these pi electrons are used up to form a bond. So you have hydrogen over here. Then this gets connected to carbon. Okay, this carbon is connected to hydrogen. You have hydrogen. So when this bond comes and attacks here, oxygen takes up the electron. So it is O minus, and then you have positive charge getting generated over here. So now what exactly happens is this hydrogen gives its electron, and then it comes and gets coordinated, or not coordinated, or linked with this O minus, as a result of which we get this particular molecule, right? So this is the mechanism, very easy mechanism, very easy to understand. So what exactly has happened is this H has been converted into CH2H. This is something which could be the best possible explanation, something which you could easily remember. Now let's try and understand the structure of the polymer. So we are going to study two types of polymer. The first polymer which we are going to study is a linear polymer of this. So for drawing the linear polymer, let me draw one monomer over here. So this monomer, I would simply say this monomer can form polymers. Okay, so now let's draw the structure of the linear polymer. So now what exactly happens is you have one molecule over here. So let me just redraw it again. So you have, just make it a little bit more dark. Okay, now you have this is connected to OH. Okay, so this is connected to CH2 and then OH. Now you have another molecule. Let's draw another molecule in the same way. You have the benzene ring, you have this OH, and then this is connected to CH2OH. Now you have one hydrogen over here at the ortho position. So this hydrogen and then this OH will be eliminated in the form of water. Similarly, likewise, you could have one more molecule over here, and similarly you could have one more of the same type over here, as a result of which we could get something like a polymer like this. So let's draw the benzene ring first. This is connected to OH, right? And then this is connected to CH2. So this CH2 is now connected to another benzene ring, that is this benzene ring. So you have another benzene ring. Okay, this is connected to OH. Now this is connected to CH2, right? So that means it is going to form like more rings like this. So we write something like a line like this, indicating the formation of a polymer. Similarly, if you observe in all the ortho positions, it is CH2. So I would draw one CH2 over here and then just make the polymeric chain. So the name of this polymer is Novolac. Okay, and it is nothing but a thermosetting polymer. Thermosetting, it's a condensation polymer. Okay, now this was Novolac. Now our title says that bakelite. So now let's draw the structure of bakelite. So now let me take enough space for drawing the bakelite molecule. So you have the bakelite structure, which I'll be drawing it now. So you start with the same. You start with the Novolac polymer itself. So you have one Novolac over here. Okay, this is connected to OH, and then this is connected to CH2. This is connected to another benzene ring. Okay, this is connected to OH, and then you have CH2, and then you have a zigzag line which says that this is nothing but the growing polymer chain. Now you just draw same molecule over here, and at the para position you have OH group. Now this is connected. I would draw the molecule in the same orientation so that it's easy for me to connect it. So you have OH over here. Now you have CH2, and then this is connected to CH2 over here, and then you have this is connected to CH2. So if you observe that there is a hydrogen over here, there is a hydrogen over here, okay, and then there is a hydrogen over here as well, there is hydrogen here as well. So now this I'll treat it with one more molecule of formaldehyde. So you have plus OCHH. So now what exactly is going to happen over here is water molecule will be eliminated. Here also water molecule will be eliminated. And finally, the two structures will come together, and this is nothing but the structure of bakelite. So now let me just draw the final structure of bakelite and see how it goes. So you have one benzene ring. This is connected to CH2. This is connected to another benzene ring. Okay, and then you have a CH2 over here. This is nothing but the growing chain of the polymer. And then you have an OH over here, you have an OH over here. Okay, so this is nothing but the polymer. Now you have the bottom chain. So let me draw another chain. Now this is connected to CH2. This is connected to one more benzene ring. This is connected to CH2, and then you have the growing chain over here, and then you have OH over here, OH over here. And then this is connected to CH2, so I would simply draw it this way. This is connected to CH2, so this is nothing but the structure of bakelite. Again, the properties are similar. It's a thermosetting polymer, it's a condensation polymer, it's a network polymer. This was a linear polymer. This is, you could say that, a network or a branched polymer. So this was about bakelite. Bakelite can be used in electrical switches, you could say CDs, laptop adapters, and you could say gramophone records to a certain extent. So it is basically a form which is resistant to heat. This is the reason you could say those electrical fuses are generally used. The polymer generally used in those electrical fuses are basically bakelite because it can withstand high temperature. So this was about bakelite. So now we'll be studying more about melamine, we'll be studying about urea formaldehyde and few other polymers. Okay, now let's try understanding the structure of another polymer, that is melamine, which is melamine formaldehyde polymer. Okay, now let's try writing the structure of melamine first. So this is the structure of melamine. You have nitrogen here, then you have nitrogen here as well. Again, this is connected to carbon, and then this is connected to nitrogen. Okay, so now you have a triple bond here. You have a triple bond here, you have a triple bond here. Now this is connected to NH2. Again, this carbon is connected to NH2, and then this carbon is connected to NH2. Okay, now let's write down the structure of the polymer which we are going to study. Not the polymer basically, but let's try writing down the structure itself. So now as I have already discussed that a hydrogen, right, this converts to CH2OH when it is treated with a formaldehyde. I have shown the bond hydrogen because you have nitrogen, this is connected to hydrogen. So now what exactly happens is you get this structure. You have nitrogen over here, this is connected to carbon, this is connected to nitrogen, this is connected to carbon, and then this is connected to the nitrogen, right? So now again, let me put a triple bond over here. Let me put a not triple bond, double bond over here. Again, let me put a double bond over here. Now you have this N. This N, it is connected to H2, right? So this H, okay, this H will be converted into CH2OH on treatment with formaldehyde. So you have H, C double bond OH, right? So this one of the H will be going and getting bonded over here, the carbon will bond over here. So you have NHCH2OH, right? Similarly, you have an H and then here N. This is this will become NHCH2OH. Again, the same thing. This N, it is connected to H, and then this hydrogen will be becoming CH2OH, right? So this is nothing but the monomer. Okay. So now let's try writing down the structure of polymer in the same way. So now how exactly the polymer is going to look like is very simple. You take the molecule like this. So this is connected in this way. You have double bond here, you have a double bond here, you have a double bond here, and then you have something like this. This is connected to NH, and this is connected to CH2. Okay, so now this is connected to CH2. So this may condense with one more molecule, as a result of which this OH will be eliminated. So I would write the growing branch over here. Similarly, you have this NH. Okay, now you have this is connected to CH2. So I'll write it CH2, and then this is nothing but the growing branch, because this may condense with one more molecule. Similarly, even the same thing could happen here as well. So you have N, you have H, this is connected to CH2, and then you have the growing branch. So this is nothing but the structure of melamine. Okay, now where is this melamine used? First of all, let's study the properties. So the first property, it is thermosetting. Thermosetting polymer, it is condensation polymer, it is copolymer or homopolymer. Because copolymer, if you consider the reaction over here. Homopolymer means it could be copolymer if you consider HCHO as one of the unit, but if you could also say that it is some sort of homopolymer, because it is nothing but it condenses with the molecules of its own type. So it is better not to classify it in terms of the number of monomeric units. Then you have the next, it is resistant to heat, right? Then with you have seen this polymer, basically melamac, in beautiful crockeries. So if you know that these crockeries like cup and saucer, you could put a heated liquid like something like hot tea or hot coffee or anything, and it won't melt, right? Similarly, the moment it falls down, it breaks, right? So this is nothing but an example of thermosetting polymer, which is melamac. Okay, now let's discuss about the urea formaldehyde and the other condensation polymer. So now let's start with urea formaldehyde. So now urea is represented as CO NH2. So I would write this as NHH. Then you have NHH, right? So now what exactly happens when this is treated with HCHO? I have already discussed, H goes to this O and C comes and takes its place, right? So similarly, the same thing would happen for this hydrogen, this hydrogen, this hydrogen as well. So finally, you would be getting something like this, wherein you have C double bond O, you have N, this is connected to N, then H will be converted into CH2OH. So you have CH2OH over here, you have CH2OH over here, and then similarly you will be having CH2OH over here, right? So now this chain will keep on growing on and on, as a result of which now this will again react with one more molecule of urea, NH2CO NH2. Now what exactly is going to happen is this OH and this H would go in the form of water. Similarly, the chain is going to grow, right? So there could be different possible combination, different structure. The simplified structure could be written as NH, and then you have CO, then you have NH. So this would be connected to CH2, right? This would also go somewhere like with the other molecule. So simply I could write it as CH2 and then put a growing chain over here. Similarly, you could write a CH2 here as well and put the growing chain, right? So now if you start with n such molecules, you get something like a polymer in which this is nothing but the repeating unit. So urea formaldehyde is generally used in the plastic chairs which are used for sitting, like, so they are basically urea formaldehyde. It has its other uses as well. So properties again, it is a network polymer, you would say, and it is a condensation polymer. Okay, and then it belongs to the category of those network polymer which we have already discussed. Now the last part of the polymers, like not polymer section entirely, but the last condensation polymer which we are going to study is nothing but glyptal. Okay, in the case of glyptal, again, it is a copolymer, and it is nothing but a polymer in which you have this compound. So you have C double bond O, OH, and then you have C, double bond O, OH. This is nothing but phthalic acid. So this condenses with a molecule of GLY. It stands for glycol. So you have HO, CH2, CH2, OH. You could do the reaction the same way you have done pterylene, and then I'm just going to write down the final structure of the polymer. So you have the benzene ring over here, and then you know that this OH normally goes off. So I would simply write this as C double bond O. So this is one chain, and then you have this C double bond O. Let's say if this condenses with the molecule of ethylene glycol, then you have something like O, then you have CH2. So H and OH goes in the form of water. So you have CH2, CH2, and then you have O. So if you see this even the condensation can happen here as well, right? So that means this OH can go with this H as water. You could see the condensation. There are different possible combinations that could happen. So this is nothing but the polymer glyptal. So when you start with n such molecules, you get the molecule glyptal. Again, the properties, you could say that this is a condensation and this is a copolymer. Now the uses. So this is used in manufacture of paints and lacquers as well. Okay, paints and so this was about the session on condensation polymer. So our next session is going to be about synthetic rubber and biodegradable polymer, not extensively, but yes, we would like to, we like to introduce different concepts like what are the different types of polymer, biodegradable, non-degradable, as well as how a polymer could be formed. So that we'll be learning in the next session wherein we'll be discussing about the synthetic rubber.